Hello, Vito.
Okay, so I think, yeah, all of the people are in the Zoom chat. Let's just figure. Okay, so yeah, Juan has already activated the YouTube as well. So yeah, I guess we can start with the tutorial.
Yes.
Okay, so hello also to the people that are in YouTube. Okay, so well, I think this time we didn't send you we didn't send you an email with today's PDF, because in reality there's not going to be too much that's going to change with respect to what is on the website. So for the people that are in Zoom, yeah, the usernames and the password are going to be the same as usual, also your machines. Please, however, let me know in case you cannot access, in which case I can write you the credentials on the Zoom chat. But yeah, but basically the tutorial is going to be as usual on the website, on mobilechem/communications website. Okay, so at this point, I think we can start properly. So I'm gonna share the screen now. Okay. So can you see the screen?
Yes.
Okay, awesome. So yeah, as I was saying before, so yeah, the PDF is going to be here in communication. So mobilechem.com/communication, and here it is. So computation of Redox potentials. As usual, we are going to follow pretty much step by step what that is written there, and yes, there is part of the material that we prepared for this lesson. Now there's going to be another part, and the main reason is because this time we are going to need a trajectory. Actually, two classical molecular dynamics trajectories that I have previously run. This is especially for the people that are in the YouTube channel. Of course, the people in Zoom have access to all the material in our machines. But yeah, in the case of the YouTube channel, I have prepared a GitHub page, which I'm gonna copy paste on the chats. Here, yeah, I'll paste it now. I think I have it here. Sorry for the duplicate. Okay. So in this page, you're going to find the folder, which is called free lower bar Redox, which contains all the scripts that we're going to use throughout the tutorial, and also contains the classical molecular dynamic simulations that we're gonna need. This is the first thing. This for the YouTube people. The second thing is something actually I didn't think of before, and I also have to apologize for that. So we are going to use Amber, Orca, mobile tools, and this you already know. But within the interface of Orca, we're going to use a program which is called XTB. Now, XTB is a program that allows you to perform some kind of semi-empirical quantum mechanical calculations, although I'm not entirely sure whether that's precise, because it uses a method which is more often used in solid-state physics, which is called the tight binding method, but applied to molecular systems, as in our case. So yeah, I have posted in this GitHub page all the instructions on how to install it. the environmental variables to put and all that stuff. So of course, for the time being, you don't need to do this right now. We will have time at some point throughout the lecture in which you could eventually do so. It's quite easy, but nonetheless, it's okay. It will take you like 10 to 15 minutes at most. So you can do it while the molecular dynamic simulations we're going to run are well, running. Okay. So yeah, and apart from that, please download. Well, you can either git clone the entire repository, or simply download these 3 lower bar Redox. Let's minimize this thing. Lower bar Redox folder. Okay. Okay. So now that we are there, let us first begin with what we are going to do today, which is the computation of redox potentials using quantum mechanical, molecular mechanical methods. So we are going to start with a small, small PowerPoint presentation, which I have also posted in exercises here /doc. So here you can find the PowerPoint, well, in PDF format, of course, but yeah. So you can eventually easily follow it. And also, well, here you can also find, again, the PDF of the entire exercise. Okay, so they are here /doc. So remember, this is this repository. So it's just github.com/mobilechem/exercise. Okay, so let's go now to the point. The main goal of this tutorial is for you to somehow learn how do we apply the sampling techniques and at the same time QMMM techniques to compute this quantity, what we call redox potentials. Now, this thing is perhaps people who have done chemistry or any other scientific subject in which you had like a chemistry and introductory chemistry course, most likely have seen these redox potential stuff in their lives. But nonetheless, let's just recap because, yeah, you know, eventually it's been a whole lot of times in the last time we saw it. Oh, but by the way, please, yeah, ask questions, of course. During this presentation, I'm not going to be able to see the questions, but afterwards, I'm gonna turn on share it on the screen, so I will also be able to see all your questions. Okay, so what are these famous redox potentials? Well, in this case, in today's lesson, we're going to study what we call an oxidation half reaction. So this is quite an intuitive process. We're gonna study this molecule, which is called the noradrenaline, which is the molecule you actually have to do on the first exercise with Vito in the nice introduction to classical molecular dynamics. So what we're gonna do here is we're gonna study its oxidation process. So basically, the loss of an electron by this molecule. Okay, it's a quite simple reaction. We call it half reaction because, of course, these reactions do not occur, well, not naturally, at least not in what we call the usual conditions. Of course, I'm abusing language. So this thing in reality is coupled with the oxidation of a different species. Okay. So here, however, we're going to study just the, sorry, I said oxidation, I meant the reduction of another species, which will receive this electron. So here we're going to have to do only with the oxidation part of this molecule. Okay, now in the literature, you're going to find most of the times and also in the standard chemistry textbooks, you're going to find this quantity here, which is usually reported in electron volts, or which is the potential, or let's call it with this language like the voltage that is kind of generated once this electron is missed. So this is called well, this is the oxidation potential, from reduction to oxidation. But in the literature, you're going to find the quantity named as reduction potential. So basically what we're measuring here is somehow the energetics of the opposite process. So the reduction of the oxidized species. And this is done simply because the potential of this reaction is precisely the opposite of the potential of the opposite reaction. So the opposite in terms of, from a mathematical point of view, minus this guy here. So by convention, people always report these potentials as reduction potentials. That is referred to the reduction reaction. So basically, although our process, the process we're going to study is the oxidation, we will compute these redox potentials like this. So reduced species minus the oxidized species. Okay, so after this premise, yes, I said before, we're going to focus on that process. So what do we do in practice? How do we get this so-called redox potential? Yeah, this is what I said. So the reduction potential, which is the potential between the reduced species minus the oxidized species, is simply the so-called redox potential. So there is this nice equation here which relates this redox potential quantity with the Gibbs free energy of the reaction. So remember that for a reaction, we always have associated with it a Gibbs free energy. So basically the thermodynamics of the process. So now we can see that there is a direct relationship between these two guys. So we can compute this guy here by computing this Gibbs free energy. Okay. So in practice, we are going to compute this guy here. Now, perhaps you will have already noticed that since we are talking about Gibbs free energies, we will need sampling, right? So let's see how do we tackle this problem here. Now, please notice that in this case, we are having a chemical reaction. This means that the reactants are going to be different from the product. So we're going to have two different chemical species. I'm saying this redundant things because we really have to emphasize this for the reasons that we're going to see. So since we have two species, one oxidized species and one reduced species, of course, what we know as the potential energy as a function, sorry, yeah, sorry, these labels are wrong. This should be the energy and this should be a geometric coordinate. But yeah, what I mean here is basically that these two guys are different species and as such will have different so-called potential energy surfaces. Okay, what does it mean? What does it imply? Well, it implies that when we perform sampling, we're not going to perform sampling on a single molecule. We will have to sample let's call it the phase space of this oxidized species, but also the phase space of this reduced species. And we're going to compute this delta G as the energetic differences between what we obtain from these two simulations. So as I said before, so we have to sample the two species. Okay, now let's go to the practical point of view. So how do we compute this? Well, intuitively, and people sometimes doing literature, we also have done it sometimes, is simply compute this Gibbs free energy of reaction as the difference. And at this point, I point out this notation. So the difference between the average energy of the reduced species minus the average energy of the oxidized species. So what does it mean that I compute averages? Well, it means that, of course, I'm considering ensembles of, let's call them geometries in the configurational space of each one of these species. Now, I have also put this guy here for completeness. Well, as you can see here, perhaps, these are two ensemble averages. And this guy here is the so-called Gibbs free energy of the solvated electron. Now, this is a quite small correction that people tend that needs to be put, because in the reaction that I showed you at the beginning, we have the oxidation process. And this means that we not only have the molecule in the reduced state and the molecule in the oxidized state, but we also have this electron, which when leaves the molecule is well, somewhere else and is solvated by the rest of the environment. So this is this energy here. This has to be put whenever we consider half oxidation or reduction reactions. Now, this is just a constant. So this is like 0.83 kilocalories per mole or something like that. I don't remember. We're not going to put it today. So because, yeah, it's just a scaling factor. And for our purposes, it's not that important. But I said it for completeness. So we are going to compute this magnitude here. OK, so we're going to perform sampling here in the reduced species and sampling here in the oxidized species. OK. Okay, so now let's go to the final slide, and then we will start the tutorial properly. So, okay, what are we doing here? What are we gonna do here? Now, as I also presented like more or less 2 weeks ago, what we do here is we have a molecular dynamics trajectory, okay, for each one of the species. Notice that I this time have reported either picoseconds or nanoseconds. Now, I'm going to thoroughly emphasize these two time scales here. The reason is because these molecular dynamics can either be performed with a classical force field, like you did with Vito's tutorials, in which case we can get to the nanosecond timescale. Of course, we didn't last week because we will need more time. But also, you could also perform molecular dynamics with a quantum mechanical potential. So in practice, you can propagate your trajectory considering quantum mechanics, molecular mechanics. This is what you saw with Huang Huang in his last lesson. So you have a quantum mechanical region, which is described by solving Schrödinger's equation, and the environment is described by a classical force field. Now, of course, this computation, so the entire simulation is going to be far more expensive than with a classical force field, and these are attainable at most at the picosecond time scale. Okay, so that's why I emphasize this thing. So we are going to have a trajectory, and this trajectory could have been obtained, sorry, either through a classical MD simulation or a quantum mechanical, molecular mechanical MD simulation. Now we're going to do both things in this tutorial. Of course, we're not going to predict accurate redox potentials because we would need more time, computational time for the molecular dynamics, and we will also need computational time for considering like rather accurate quantum mechanical methods. We're going to use XTB for those methods, which well is not bad for some things, but it's an approximation. Okay. So as I said before, well, this is as I explained it the other day. So we have a MD trajectory, regardless of however we obtained it. And if we are interested in ensemble properties, like the average of the energy for the redox potential, in this case, we get the energies on some snapshots of this trajectory, and then we get the distribution. And in our case, we are just going to average them. Okay. So the tutorial is going to be subdivided into two parts. Oh yeah, well, here, remember that here we have the QM region, and the environment is going to be the so-called molecular mechanics region. the low level of theory region. Okay, so the first part of the tutorial is going to be one of the things that I mentioned here, a QMMM, molecular dynamic simulation. Okay, so we will perform one of these simulations for the reduced molecule, one for the oxidized molecule, as I said before. To do so, all we have to do, quotation marks, of course, is, well, we have to distinguish the, let's say, the potentials of the two species. And how do we do that in this case? Well, for the quantum mechanical region, all we have to do is define its charge and its multiplicity. So of course, in the reduced case, we're going to have a charge equal 0, so it's going to be a neutral species, and spin multiplicity 1 because it's a singlet. Now, in the oxidized case, as you can see, this is going to be +1 because it's going to lose an electron, and it will have spin multiplicity of 2. So with these two parameters changed for the quantum mechanical part, you are going to obtain different, of course, the sampling is going to be different for each one of the species, and you're going to have two different potential energy surface curves. Okay, so this is our first part. We're going to compute the Redox potential there. The second part, now again, also in this case, we're going to need two different potentials because otherwise, of course, we would be sampling the exact same thing. However, here the distinction is done in a different manner because we no longer have, let's say, the quantum mechanical description. So the Schrödinger equation for the QM part. But instead, what we're going to have here is two different classical force fields. Okay, so one force field for the reduced species and another one for the oxidized species, because the geometries are not going to be the same. They're going to be different. Molecules are going to, sorry, two states are going to move differently from one another. So we will need to construct one force field for the reduced species, which we're going to do. Actually, you already know how to do that with Amber, and another one for the oxidized species. Okay, so in practice, the only thing, again, that we're going to change here between these two guys is just the charge. So the point charges are going to be different. Now, of course, well, you don't see it, but the expression of the force field is more complicated. But for the sake, of course, of easiness for the tutorial, we are going to use just different point charges here and here. Okay. Okay, so with this, I guess we can start. And I'll see whether there are questions. Oh yeah, one last thing before I finish is that usually when people do QMMM MD, they do prior to the actual QMMMD production a small classical molecular dynamics simulation, so that we start with a more or less equilibrated geometry. So we change from classical MD to QMMM MD. And this is actually what we're going to do here today. Okay, so that being said, I guess we can start with the actual tutorial. I'm going to stop sharing this screen. I'm going to share another screen. So yeah, if I can still find this thing. Okay. So just sorry, I'll just need 1 second. In the meantime, well, let's see whether there are questions now. Okay. So let's access from here. Open. Accept. Okay, I think it is not allowing me to access from here. Okay, it's not going to be a problem. Let's just do it from here. Okay, so I'm gonna share this screen again. Just one sec. Okay, here we are. I'm gonna change a little bit the layout here. White. Okay. So here we are. I hope you have been able to access. If not, of course, please let me know in the chat. Now, so we are gonna go to the sorry. So here, as usual, we're gonna go to the data/tutorial folder, and well, I'm gonna build a folder for myself. So let's make an ls -ltr to see if we're all here. So let's copy the tutorial samples folder, which in this case, yeah, it's gonna be called, sorry, 3 Redox. So let's copy this folder here, 3 Redox, in our working directory. -r, so I'm copying it here. Okay. So as you can see, we can see the 2 parts of the tutorial. So the first part is going to be a QMMD simulation, as I said before. And the second part, now in the second part, what we are going to do is we're going to use 2 classical MD simulations, and we are going to perform so-called single point QMMM computations on an ensemble of geometries obtained there. Now, before we go to each one of these folders, I know you already have the material, but yeah, nonetheless, let's take a look at the architecture of well, of the folders as usual. Sorry, it's not this one here. Let's just put this guy here. Okay, so here's the architecture. Perhaps it might look a little bit more cumbersome than in Vita's tutorial, but I promise it might even get a little bit boring because it's going to be repetitive, which is nonetheless good because you're going to redo some things that you have already done. And yeah, at the same time, we're going to learn some new stuff. So this is the 3 Redox folder. Within the folder, we have the QMMD, so the first part and the second part. Okay. Now, within the first part, we have a reduced folder. You might not see it that well. Let's enlarge it, and an oxidized folder, and also a script we're going to use. It's a Python script. I suppose you all have Python installed on your PCs. Okay, so within the reduced folder, we will have the system and run. So in the system folder, we will have the exact same structure that we worked with last week, and the input file for TLEAP to prepare the topology file and the initial coordinate file. The run is, of course, the MD simulations. Now, please notice here that we have minimization, heating, and MD. Now, these three guys, we're gonna perform these three simulations using a classical force field, as I said before. This means that we are gonna prepare, well, of course, a classical force field topology and also the corresponding coordinates from scratch. For the QMMM.in, we are just, well, we're gonna do what I said before. So QMMM and running the MD simulation. Now, this perhaps is not that interesting, the reduce, because it's the same thing that we did the other day. The more interesting one is going to be the oxidized, because at this point, as I said before, we will need a different force field here from that of the reduced species. This means that we are going to obtain different point charges. And at this point, we're going to put our hands for the first time on the Orca software. So we're going to perform a quantum mechanical calculation. So this we will do in order for us to obtain, as I said before, point charges for the oxidized species. Now, these charges should be different from those from the reduced species. So here we're using the GAF force field. So here to the left, here we're going to use the GAF force field, except for the point charges of the noradrenaline. So this is what we're going to do here. We're going to launch a quantum mechanical calculation, and then we are going to, again, perform the same simulation as here, okay? I'll show you in more detail later what we're going to do. In the second case here, the QMMM single point, we already have the trajectories and the topology files for the reduced and for the oxidized species. Now, for completeness, I tell you that these have been run classically for 10 nanoseconds of simulation. So here we're going to use, we're no longer going to, I mean, we had used Amber here, but what we're going to do is we're going to retrieve 100 geometries from the simulation and use the mobile tools package to generate the input files. This for the reduced and for the oxidized species. So we're going to get more into details later on. But for the time being, this is the architecture of our tutorial. So, okay, are there any questions, some perplexities? If not, then let's go ahead. Of course, you can ask questions by simply turning on the microphone. Otherwise, if there are questions in the YouTube channel for the time being, I'll ask anyone to please let me know. But okay, so let's go. Now, the first step, let's go to the 1QMMM MD folder. As you already know, here we have reduced, the oxidized, and the Gibbs script. So let's go to the reduced species. And well, let's go to the system folder. So we're going to prepare the system, the simulations. Let's see, what do we have here? Let's minus LTR. So we have the PDB file of the reduced species. This is the exact one that we used for in Vito's tutorial last Tuesday. The only thing I changed it was the atom names. But apart from that, it's pretty much the exact same guide. So the first thing we're gonna do is this is gonna be pretty much the same things we did the other day. So the first thing is we're gonna generate a so-called mol2 file which contains the coordinates that are here, but also some point charges. Now these point charges, of course, are not really quantum mechanical charges. These charges we're gonna obtain with a semi-empirical method. I think we did so also the other day. So the software we're going to use is Antechamber. Okay, Antechamber. So we give it the input file. like red.pdb, the format of the input, is O, red.mol2 minus FO, mol2. I don't know why it asks the format. I think it's because, yeah, so that it doesn't require the suffix here. With, I don't know. Then minus AT, which is the atom type, so GAF. And the charges minus C here, which is going to be BCC. Okay, so you will see at some point that it will show this thing here. So this is using a so-called semi-empirical method to obtain these charges. It's like a rough approximation for a quantum mechanical method. Okay, so let's see what we got. So, okay, of course we have a lot of other files which are not going to be necessary for our discussion. If you want, you can remove them, like star, sorry, or M, A, star. So it's going to remove all guys starting from uppercase A. And the really interesting file here is going to be the mol2, big red.mol2. Okay, so if you open it, well, it just, as I said before, show you the coordinates, the X, Y, Z coordinates, the atom types, which are the GAF atom types, because we told it to do so, and the point charges that it has generated. So each atom, as you can see, has associated with it a point charge. So there's nothing new here with respect to what we did the other day. The next thing, so we have the charges, we have the coordinates, we need all the parameters, which are the bonding parameters. So the equilibrium distances between atoms, the force constants of the bonds, of the angles, and so on and so forth. So of course, we're going to use TLEAP to do so. Here's the input. We're going to call the GAF force field from our Amber installation. But of course, there might be some parameters which are not present, and we have to complement for them somehow. So for this step, we're going to use parm chk2. So minus I is going to be the mol2 file we have just generated. Minus O, we're going to call this guy .frcmod. And I think it is minus F, which stands for the format of the input, which is mol2. Okay, it doesn't say anything, but of course, it will have generated the file we're interested in. So this is the .frcmod. Okay. So let's just take a look at that. So I think this is the exact same thing as last Tuesday. So it has generated 2 extra improper parameters. Well, these are torsion angles. So yeah, it somehow fetched them from the GAF force field from different species that have already been tabulated there. Okay. So at this point, perhaps already now, we have all the ingredients to generate the topology and the coordinate lines. So we're gonna use TLEAP. So it doesn't have anything special in the sense that well, here I'm telling it to use the GAF force field. So this is this source command as usual. By this time, if you were here from the very beginning of the tutorials, you already know where this guy is. We are also using the tip3p parameters. So we are calling them. And okay, so here we're giving it as input these 2 files. Notice that in this case, this is going to differ a little bit with respect to what Vito showed you the other day. because here I'm not generating a lib library. You can also do that, in which case, for future simulations, you can already just call the lib file. But if you don't do that and you have at your disposal these two guys here, you can just call them the way I'm doing here. Okay, so we're gonna generate again as octahedral box, and yeah, we have already seen the syntax of these guys here. Okay, so these are the two files that are going to be generated. So topology, coordinates, and we are also saving a PDB for the sake of completeness. Let's say it eases the visualization as well, because when you visualize your system, you can just open VMD and give this guy as input without putting these two guys as arguments. Okay, so the execution here is simply tilip -f tilip.in. And this is what it will have given you, most likely. Okay, so let us now see what it generated. Oh. If it generated this guy here, which is the coordinate file, of course, you already know what this guy contains. It's just the x, y, z coordinates for each one of the atoms. This is somehow called flattened, in the sense that it's kind of in a 1D vector format. Of course, you see a matrix here. You don't see a 1D array, but in practice, I think what the program does is it creates a linearized array here, in which this is the first atom, then this is the second atom, then this is the third atom, and so on and so forth. So linearized in the sense that when it reads it as a 1D, one-dimensional array, a vector. The topology, you already know it. So it's this is this guy here. So it is gonna contain the point charges. It's gonna contain the bonding parameters, and it's gonna contain the van der Waals parameters. I see a question here. Okay. Of course. Yeah. So it is tilip. Oh, by the way, please let me know if you can properly visualize the screen. Also, if I'm going fast or slow, in either case, please let me know. So this is the command, tilip -f tilip.in. Okay, I can just run it again. It's not going to give any issue. -f stands for file or input file, and you give it the name of the input file. Okay. And if everything went smoothly, this should have generated this guy here. Okay. Now, at this point, I think we can, yeah, we can. Okay, yeah, let's take a look at these guys here. I mean, it's just going to be our molecule or solvated molecule, but for the sake of completeness and for the sake of seeing that it has created what it had to create, let's take a look at what we did. Now, I will have to copy it to my local directory because, yeah, unfortunately, my large PC is not working for some reason. So it's pretty much the same thing that you're going to do as well on your local machines. Okay. Sorry, give me just 1 second. Okay, so I'm gonna copy it here. Sorry for that. I just need to remember where this guy is. Okay, so here it is. system, and this small red there. .pdb. Let's copy this. Okay, this for some reason is not working. Okay. Yeah, there is. BMD and molred.pdb. So here it is. Okay, so we have already used BMD plenty of times. So as you can see, it is kind of a truncated octahedron. So it's not quite an octahedron because you have it truncated at all its how do you call them, vertices. Okay, so we know how to do this. We go to graphics, representations. Okay, I hope you can see this thing here. So this upwards. Let's create a new representation here. Then let's call it res ID 1, because the residue we're interested in is going to be the first residue. Enter. And let us give it a different representation method. Drawing, sorry. Let's call it licorice, and you can see that it somehow has emerged there. So this is our guy. You probably recognize it because it's him, noradrenaline. It's different from adrenaline because adrenaline, I think, has a methyl group here, but I'm not 100% sure. Well, not here. Like instead of these, one of these hydrogens, but I'm not entirely sure. Okay, so this is the guide. The important thing here is that for the QMMMD simulation, you can better see what's going to be quantum mechanical. So only the thing that is more nicely represented here, and the rest of the things are going to be represented by a classical force field. Of course, this doesn't have to do with the representation and the drawing that I have chosen here. It's just to better show you what we're doing here. Okay, so let's close this guy here, and let's go back to our tutorial page. So here we are at the system folder, and now we're gonna run our molecular dynamics simulation. So let us at first copy the two files we're gonna need for it. So if you remember, the coordinate file, the topology file. Please don't press enter here. I'm just copying these two guys to the other, to the second directory. So I do -- to get one directory up, /, and then we will copy these in the run directory. Okay. So then let's go to the run directory. And what do we have here? Let's make an ls -ltr because I like listing stuff. So this ls -ltr also provides me with an ordering of the files from the oldest one to the newest one. Okay, so here we have the 4 inputs which have the suffix .in. Now we're going to do the useful thing here for molecular dynamics. So we're going to perform a minimization. Then after the minimization, we'll go to the minimum of our, let's call it potential energies landscape or surface. We are going to perform a heating because we're going to take that to 300 Kelvin. And then we are going to perform a production. Now, remember that in the previous tutorials, we called it production. Here, I just called it MD, just to distinguish it from the QMMMD, okay? So in practice, like if we were performing 2 productions, one classical MD production, that is one with a classical force field, and the second one with the QMMM production. Okay, so I think I have also reported these files in the manuscript. So I'm not going to go through each one of those guys because Vito has very thoroughly covered them. He has also nicely explained them, and they are also written in the previous tutorials. So if you're further interested in what's happening here, please take a look at them, both the manuscripts and Vito's lessons. We're just going to take a look at this QMMM.in because this is the guy who's really going to be the interesting guy for today's tutorial. Okay, so let's see what's inside. Okay, so the first thing is, well, there is the usual control section, just called CNTRL, introduced by an ampersand. And here is where we're going to define all the parameters for the molecular dynamics simulation. Okay, so remember, this is always molecular dynamics. So here we're solving Newton's equations of motion. What's going to be the important part here? Well, of course, yeah, you can take a look at all the parameters we're setting here. In particular, the simulation is going to be in the NPT ensemble, just like any other production simulation. And yeah, in reality, this guy here is kind of a copy paste of Vito's input file. So yeah, I was a little bit lazy there, I have to confess. One important thing here, look at the NST lim, which is the number of time steps we're gonna perform. So we're gonna perform just 100 time steps. Why is that? Well, this is QMMM. So whenever you do quantum mechanical calculations, they're going to be far more expensive than molecular dynamics calculations. We're going to see this in a while. We're going to compare the simulation times of the MD and the QMMM. So still, it's going to be 100 time steps. So this is 2 femtoseconds time steps. So overall, we're going to have 200 femtoseconds of simulation, which is a few time steps, but for the sake of the tutorial, it's going to be good. And for QMMMD method, well, it's kind of a good equilibration, let's say. Okay. I think. Okay, so this was the first thing. The second thing, now, all this stuff here up to this point are related to the MD simulation. Now, here is this this keyword here. So this is the keyword that will activate the QMMM. So we are telling this guy that we want to consider a part of the system as a quantum mechanical piece of the overall system. Now, of course, we have to specify which part are we considering quantum mechanical. So after we finish the control section, we go to the QMMM section. I think Vito has already covered this thing as well. But for the sake of completeness, again, I'm showing it here to you. So here is where, so this ampersand QMMM is giving you the general settings for the quantum mechanical part of the system. Okay, so here we have the first one, perhaps the most important one, in my opinion, is the QM mask. So you perhaps have already heard of the word mask in Amber. So mask basically means so what atoms are you selecting for a specific task? So in our case, we're using the Amber syntax, 2 points. Sorry, this guy is called colon. So colon 1. So this means we're gonna take a residue, and we're gonna take just the first residue. This is very important. You have to know which part is gonna be on your quantum mechanical part of the system. So Amber is not gonna decide for you Well, honestly, I don't know whether there is a default, but I wouldn't put a default because you should know what part do you want as quantum mechanical. Then there is this setting, is QM charge. Actually, in the well, oops, sorry. There should also be another guy here. Don't write it down because it's not necessary. We're gonna see it on the simulation of the oxidized species, but this option is the spin. You have to define the spin multiplicity of your QM part. Now here it's gonna be 1 because we are talking about the reduced species. Now I didn't put it here, and it's not gonna change anything at all because by default these two guys are set in amber. So I could also have not written that, and the simulation would have been the same. But I'm putting them because for the oxidized part, I think you have already grasped that they are going to change, right? Okay, so yeah, that's it. These other settings, well, they are more technical. Actually, Vito covered this, the QM cut, which has to be smaller than half of the box. And yeah, we need this guy here to be set to 0 to perform the simulation. Finally, this QM theory. Now, in the first exercise, you did a PM6 simulation. So there you were using the PM6, which is a semi-empirical method implemented in Amber. So you just used the Amber software. Now, in cases where you want to call a different quantum mechanical software, like Orca in our case, you will have to call this extern keyword. Okay, so it's all in here. And afterwards, you close the QM section, and this section, sorry, there is yet another section that will yeah, that will define which software you're using. So here it is called &orc. But if you want to use any other quantum chemical package that, of course, has an interface with Amber, this keyword is most likely going to be different. So, for example, if I don't know, there is one with Gaussian, in which case the keyword is Gau. There is one with Terrachem. There is one with well, all the software, MWChem, and so on and so forth. So we're using Orca today, and we are going to use a method which I talked before about, which is this XTB type binding. So basically, we are calling Orca, and from within Orca, Orca is going to call this XTB. However, notice that you have to install XTB as well to do this thing. Okay.
Gustavo?
Yes?
Can I make a question now?
Sure, sure.
Yes. I was wondering if we want, for example, to study the interaction of our molecule and the first solvation shell, for example. Could we set this system in the QM mask part, for example, or we have to change our PDB file to set this kind of QM part?
That is actually an excellent question. Because, of course, if so I'm going to suppose that with interactions, I mean, I don't know, do you mean interactions in the sense of interaction energies? I mean, between for example, the first shell of waters and the system let's say our molecule?
Yes. If, for example, we want to study the non-covalent interactions between our solute molecule and the first solvation shell or second one, and so on. Because I was thinking, for example, if in this case our system, the QM part is only the solute molecule. But if you wanted, for some reason, to study more deeply the interaction of our solute with some part of the solvent and the rest of the solvent that's far from this solute in a treatment.
Yeah. Okay. Then yes. Now you don't have to change anything on your PDB, or for that matter on your topology, because the topology simply gives you the information about what atoms are in the system, what are the corresponding point charges. Now, this is one step ahead in the sense that here you choose which atoms or which molecules are going to belong to the QM region. So of course here we're putting the 2.1 because we just want the solute to belong to that region. But if you want to study that kind of setting, then yes, for example, this is something actually quite interesting. If we have some time, because this is a thing as well that also MoBiochem does. Now here, sorry, MoBioTools. The important thing is that you have to know what is the mass of those molecules. So if you don't know what are the labels of the closest molecules to you to your solute, then you can not do that. If you do so, then yes, of course. For example, we want water molecule which is labeled number 2, number 3, number 4. Then you put it like 2, 3, 4. Sorry. And of course, this is going to include water molecules which are labeled as 2, 3, and 4 residues in your PDB file. But of course, you need to know which molecules are those there. And this is like I'm not gonna call it a drawback, but I mean, once you know that, of course, you can perform the simulation. What you said there, that to choose like the closest 5, 6, 7 molecules, this is actually something that CPP Trash does, which is the software that you have used, an analysis software you have used in the last lessons. And because it automatically finds the closest molecules to that. And MoBioTools, which is the guide that we're going to use, the software we're going to use later on, uses that feature of CPP Trash and generates the quantum mechanical input file, including those molecules. So with just Amber, you need to know which are the residues you want.
Okay. Thank you.
You're welcome.
Gustavo.
Yep.
So can I say something?
Sure.
Because maybe, I don't know if maybe he was asking for doing this along the dynamics, maybe including the solute and maybe some solvent atoms in the QM region during the dynamics. If this was the question, then you, as you said, you can define not explicitly the molecule numbers you want to include in the QM region, but you can define a cutoff. You can say, I want the molecules which are within a sphere of 5 angstroms in the QM region. You can do that, but then you need to use a special treatment which is called adaptive QMN. I wrote here in the chat, which is implemented in Amber indeed. And here, in case you are interested, here you have a paper where they explain how to treat solvent molecules in the QM region. And you need a special treatment because not all the time the same molecules will be close to the solute. So some molecules will diffuse away, other molecules will come closer to the solute. So you need to, let's say, treat different molecules at different times in the QM region. And for this, you need a special, let's say, formulation, which is called adaptive QMN. Okay, so here you have the paper in case you are interested.
Okay, thank you. And it makes more sense because some molecules will change their position, maybe going to the part.
Yeah, you need to define then a cutoff, but the problem there is, for example, at a particular time step, you can have maybe 10 water molecules in the QM region. And then in the next step, you will have 12 because 2 has diffused, right? But as you are having different number of molecules in the QM region along the time, so your energy is changing a lot. And you have discontinuities in the potential energy surface. So So you have discontinuities along your trajectory in the energy. So you need to do this special treatment in the frontier between the MM region and the QM region. But in this paper, it is well explained. Okay.
Okay, thank you.
Thank you, Juanjo. There is indeed the adaptive QMM possibility. Yeah, of course, I think in that case, there is a buffer region needed to account for this difference in this. So there's also the possibility of defining. I don't know because I've never used it. There should be a possibility to define the size of that buffer region, right? Might be the case.
Gustavo?
Yes?
I have another question.
Sure.
So if I understood well, if you wanted to have to treat them, for example, the first solvation shell in the QM region, so it's better to use this adaptive QMM. But if you want, for example, to have just one or two others in the QM region that make like stronger hydrogen bonds, so you can use CP-Petrage to select these water molecules, and then you just define these, let's say, two other molecules in this QM mask. Is that?
Yeah, exactly. Exactly. So you, of course, notice that in that case, again, we go back to also what Juanjo was explaining. That is, if you actually want to perform dynamics, then these water molecules, these one or two water molecules throughout the dynamics will probably go further apart from the solute. If it is for the sake of performing dynamics, I think and if you want to continue having your shell in the QM region, but that it be like the first solvation shell, then I think the adaptive QMM would be the best thing, because CP-Petrage is a post-processing feature. So whatever you do it on an already performed trajectory or on a single initial coordinate file.
Yeah. Okay. Thanks.
Thanks to you. Okay. Are there any other questions? Also in the channel, perhaps. Let's see. Okay. If not, then well, at this point, I think that we can. Let's say the changes. It's not going to change anything. We can launch this script, which is the run.sh. Let's take a look at that. Well, actually, if you want, we can launch it because it's gonna take like 10 minutes, and then we can take a look at what is inside. But you all have already seen the commands there. So let's first execute it so that the trajectory is running. So we're gonna run it in background. So as usual, we're gonna use the nohub thing, then / run.sh, and then ampersand, so that it actually runs in background. So the background is handled by this ampersand. The nohub, well, what it does is that it creates it's called a persistent job. This means that if you close the station, this job will still keep running if it is in background. I'm already used to doing these things here, but yeah, for the sake of the exercise, it doesn't matter. So let's do this, and hopefully everything will work properly. So yeah, we can see with a top that it is running. So yeah, a lot of people have already launched it, which is great. Okay, so what are the contents of this run.sh? So as you can see, it has the minimization command. So it's taking the minim.int. This, by this time, should already be familiar for those of you who have followed from the very beginning. If not, well, we are sequentially executing each of these tasks here. We are doing so automatically because what you did in command line can also be put in a script, which is what I did here. So yeah, so the script goes ahead, then does the heating, calls again Sander for the classical MD, and then it performs the QM/MM/MD. Okay, so at this point, I'm gonna ask you, because we could either do a little pause, like 5 to 10 minutes pause now, and then we can come back with our results, or we can also do the oxidation part, and then do the pause while it is running. You tell me. For me, it's the same. We can both. Yeah, the simulation. Actually, I say it's going to take perhaps more than 10 minutes because we are running several people at the same time. So yeah, I don't know.
Let's do a short break.
Okay, cool. Then yeah, I see you in like 10 minutes or at most 15. Okay, cool. Thanks. Okay, let's do that. Okay, hello. Yeah, so we are back. Of course, we had enough time for getting a coffee as well. Okay, so let's wait a few seconds eventually. And also, well, let's see if there are any questions in the YouTube channel, or if anybody has a question, as usual, let me know. Okay, if not, I think, yeah, I think we can start. Let's see, there's 2 comments in the chat. Okay. Okay, so I'm gonna share back the screen again. Let's hope this didn't disconnect. Okay. Yeah, sorry about that. Okay, so did the simulations finish? Did anybody have any issue? We can see whether the simulation came to an end or not by taking a look at the output. Now, in my case, well, if we see up to the md.out, which is the classical MD, we go to the end of the file with G, so we see that it finished. How long did it take? Like 161 seconds. Of course, this is a classical MD now. Of course, we are interested in the QMMM. Now, I already see that something happened with mine. Please, the other people, let me know if you had any issues with that. If not, then we can go ahead. So I had an issue here. Let's see what it was. Okay, so it's now it is complaining for some reason. Now, quick question: did you also have this issue in your simulations? It is quite odd. Okay, and that was just me, I think. Okay, this is not going to be a problem. Let's see. Okay. Yeah, I don't know. It might have as well have been a memory problem. Those who are in this PC, but with 0.5, have also your simulations finished properly. Okay. Okay. Cool. Well, that's just me. Okay. So I'm just gonna copy from my backup that I had. So I don't have access to that one. Sorry about that. Okay, so I'm just copying my own output in the new folder. Well, actually, yeah, it's not going to be necessary. Let's just take a look at this output here, which is going to be pretty much the same thing that you're going to have in your folders. So see the chat. Okay, no more questions. Okay. So this is the output for the QMMMD simulation. So QMMM.out. Now, again, if we go to the end of the file, we see that it finished properly, although in my case, it didn't, but that's okay, I think. Now, what's the data we're interested in from this QMMM.out? Let's go upwards a little bit. Okay, we will have all this junk, and at this point, we're going to have these RMS fluctuations. Yeah, this is really not interesting. Also, the averages are not that interesting. So the really interesting part is going to be, well, all these time steps. So in the QMMM-MD, we performed 100 time step simulations. Now, what we're going to require to compute the redox potentials here is going to be let's call it the SCF energy, which is basically the energy that you get from the quantum mechanical calculation. Now, notice that when you perform QMMM, remember that you have the QM part of the system, but that QM part is being polarized by the environment surrounding it. For using QMMM, we need to preliminarily define reaction site. Yes, we do. I mean, if your reaction site is like your thing of interest in the system. So, for example, if you have an enzyme and you want to study the catalysis of some kind of reaction, you do need to know which ones of those residues, of course, apart from the substrate, do we need to treat quantum mechanically. So you have to know what are the residues that need to be in the quantum mechanical part of the system, like we did in this case. So we knew we wanted residue number 1. Of course, in Amber, we also have the syntax mask. So if it has a specific name, for example, in our case, it is called LNR, I think. Then we tell Amber that this is the guy that we want in the QM region. Okay, so the information we're gonna draw from our simulation is gonna be this energy here. So this is gonna be called externe SCF, and this value here. Okay. Okay, great. So of course, we have one of these guys for each time step. We have 100 time steps, so we're gonna fetch it for all these time steps. So of course, we're gonna do it in a rather rough manner. We're gonna use grep because it's easy. It's just one command line, and we're gonna look for this externe SCF string. Okay, so we're gonna execute the following command. Rep, like perhaps we have already done it before. Externe SCF, you can either put this equal or not, it doesn't matter. So yeah, I'm showing the screen, right? Yeah. Then the file, so QMMM.out, and then the output is going to be energies.dat. We're going to call it that way, also because for the script we're going to use, which is this Gibbs script that I also provided you, it will take these energies as input. But of course, if you call it differently, you will have to be consistent afterwards when we execute that script. But we'll do it later on. So for the time being, let's just do this. Let's do this. Well, I have permission. Why not? Oh, of course, because this belongs to a tutorial. But yeah, it doesn't matter. Fortunately, I already have it here. So we are going to have this energies.dat file. What is this energies.dat file going to contain? Well, it will just contain this string here for all the snapshots of our simulation. Something to point out here, of course, since we're doing grep, we are taking all the external SCF entries here This means we are considering each time step of the simulation that has been printed in an output file. For the sake of this tutorial, of course, it doesn't matter. But if you want to do actual production simulations, you will have to account for some time of equilibration prior to the actual QMMMD. So basically, you would have to truncate a few picoseconds or femtoseconds of simulation in the case of QMMM. Now, for our purposes, let's go to the end of the file with G. And let us delete these two lines here. So we can just delete it with pressing DD, so D twice, then D twice, then so DD. It is not going to allow me to do this for the time being because, kind of have account permissions here, but issues. But yeah, why are we doing this? Perhaps you will have already grasped the reason. It is something I mentioned on the QMMM.out. I think this is not written in the tutorial, but of course, when we do this grep, it will take all these entries. Okay, so it will also include. We are here 100. It will also include this entry here, which is the average over 100 time steps. So we don't need this. I mean, technically speaking, this is what we're going to compute afterwards, but this is just for this specific case. So this is not a real point in our data set. So we're going to delete the last but one line and the last line. Okay. Let's see. There is a question. Is giving a positive energy. Oh, yeah. This is exactly what was. That is a really good question because it is pertinent with what I'm just saying. The reason is because we're going to delete the last two lines. So the last but one line is, as I said before, the average, which is not an actual data point, so it is not an actual time step, and the last one, which, as you said, gives a positive energy. This is the root mean square fluctuation of the energy, and it is expressed as a positive value because it's something like the dispersion of the data, but each one of the entries is going to be squared. So that's why it appears as a positive value. So we don't need this guy here, of course. Okay. Okay, there are actually two questions. Sorry. Yeah, go ahead.
Sorry. No, okay. Just a question about this RMS. Is there a threshold that we have to look always when you look to those RMS fluctuations? I mean, for example, the maximum RMS should be smaller than 5.0 or something like that, or there isn't such a kind of interpretation?
Well, there isn't a magical value in a sense, because it might also depend on the system, because depending on the complexity of the system, you might have larger or smaller values. But of course, if you see like numbers of this magnitude, and you see like a number which is 10,000 times smaller than this guy here, well, like this is just 4 kilocalories per mole. So this kind of gives you the variation of the energy of the system along the simulation. So this is a small number with respect to the absolute energies here. Now I said this guy was squared. This is actually a standard deviation. So this means you get the squares of the differences between each one of these values and the average, and then you sum them up. So you compute actually the average of these differences and then square it. So this actually has the value of kilocalories per mole. Now, we can say, yeah, it's not that large. It's 4 kilocalories per mole. It's well, it's within the thermal order of energy. It's not that large. If you see something between 50 and 100, or maybe 15, but above 100 kilocalories per mole or 200 kilocalories per mole, this might mean that there is something not quite good on the system. I mean, if your energies are more or less like this one, but yeah, there is not magical number. You have to more or less see what is the average, how your distribution is made, and see if it is really broad, then this number is going to be quite large, and then you will see, okay, this is not a good distribution.
Okay. All right. It's more or less, if I understand, we have to see if it's a small number in relation to, for example, the error of the methodology, for example. Is it the question?
Yeah. In part, yeah. So you have to see what the error of the methodology is. Indeed, this is not the large. We're also using a classical force field for a part of the system, and the quantum mechanical part is also described in a. It's good, but it's not really accurate for energies way. But yeah, I think this is a question that relates more also to the statistics of the whole ensemble.
Okay, I got it. Thank you.
Thanks to you. That was a very good question. Okay, so Juanjo has actually given us a good like estimate. So yeah, for example, if the variation is more than 5% of your energy, this is not good. Now we can do the math here.
Gustavo, I'm talking about the total energy which should be conserved along the simulation.
Okay. Yeah.
Not only the QM well.
Yeah. You're totally right. Yeah, the total energy. So this guy here. Yeah.
There is a question also in the channel.
Okay. So for using QMMM, do we need to preliminary define the reaction site? Yeah, this question had been done before. The answer is yes. You need to know what is your reaction site composed of. And then what about a simulation of cytochrome enzyme system? Monica asks. I'm not quite familiar with that system. I think it is quite large. If I'm not mistaken, like it's of course there. Well, you need to see what is the portion that you're really interested in. Now, if you're interested in the full like system, that I think that's it related with excitonic excited states, but I'm not entirely sure. I don't want to say something weird. But yeah, if your system of interest that you want to consider in a full QM region is quite large, then perhaps, yeah, you have to assess what methodology is going to be computationally feasible. So what we did was XTB, which is good for these kind of systems if they are quite large, like 200, 300, 400 atoms, 400 quantum mechanical atoms. I mean, so yeah, of course, you have to assess to compute the ratio between the computational cost and your accuracy. This is like the dilemma of all computational chemists, I think. Can you show the input file? Yes, I can show the input file. This, by the way, is okay, but yeah, sorry. I think the QMMM input file is on the PDF of the tutorial. .in. Although I think you were referring to the input of the quantum mechanical calculation. Let me know if this is the case. So the input for the QMMM, so the amber input is this guy here. Sorry, I went to the end. So we took a look at that previously, but basically it's like any other how do we call it, MD simulation. It has the control section, And in the end, you have this definition. So you say you want to perform quantum mechanical molecular mechanics simulations. Then you define these two sections accordingly. Okay, so this is the QMMM input. Now, Amber intrinsically is going to generate an input file for the quantum mechanical part of the calculation, from which we're going to get the externe SCF energy. So in this case, we're using Orca. And in this case, Amber is going to generate an input like this one. So like you're going to have also this thing in your directory. So old.org job.inp. So let's open it up. Although we're gonna take a look at this guy in a second. Now, of course, this is kind of complicated. But basically, it is going to tell you what methodology you want to use. This has way too many parameters that for the time being we're not interested in, because some of these are kind of defaults, I think, and some others, well, again, there's too much information here. So this is what Amber creates as default when it performs the QMMMD. But we'll take a look at a simple one, the one that we're going to create afterwards. Okay. Okay, so would you mind explaining the input file? I will come back to this guy here if we have time in the end. Otherwise, I'll take a look at the simpler input file that we're going to generate with mobile tools in the second part. But basically, yeah, we have the methodology and the set of coordinates and the coordinates and charges of the point charges. They are here. So methodology, it's XTB. So this thing here, XTB. So this guy is actually used to define the methodology. We're going to perform an Amber calculation, by the way. Sorry, an Orca calculation in just a second. So again, point charges, they're going to be in this file here. We'll take a look at a file similar to this one later. And the X, Y, Z coordinates here with the charge and the spin multiplicity, and a file containing the X, Y, Z coordinates of that time step. Now notice that Amber is going to save just the last but one time steps by default. Okay, so I'm not sure whether Amber has an option to saving the input file for each one of the time steps. I don't know. It might be the case or might not. If it is the case, then awesome. I don't know, but otherwise you would need like to perform single point calculations on geometries that you would be interested in. And this is what we're going to do in the second part of the tutorial. Okay, so we have the dynamics of the reduced species. Now let's go and do the same thing for the oxidized species. Now it's going to be almost the same thing, but there is one thing that is going to change. So I will go back here. So I'm using the tutorial user. So what are we doing now? So let's go back to directories back. So //. For the time being, we're not doing anything else with the energies.dat file. At this point, let's go to the oxidized species. Okay, so where are we? If you don't know where you are, remember you can always use the pwd command. So we are currently here. And so we will go to the oxidized folder /system. Okay. Let's see what do we have in this folder. So we have more files than in the previous case. So we have the tillit file again. Remember, so just to make the things clear. So we are going to perform the classical molecular dynamics, the QMMMD simulation for the oxidized species. This means that we need a different set of parameters. Now, in the practice, what we're going to change are going to be the point charges of the solute. So this is what we're going to do. We're going to do one step more than in the case of the reduced species, because we want to get these point charges from a different calculation. we're from a Hartree-Fock calculation. So we'll see this in just a second. So we have the geometry of the oxidized species. Now, this is the equilibrium geometry. So it basically is an optimized geometry for the oxidized species. Now, it is going to be different from that of the reduced species. So the geometry is different because you have a different state of the system. Basically, you have removed an electron from the other guy, so you expect that somehow the equilibrium geometry changes. Okay, so we can take a look at it. It's this is the PDB. So yeah, it's pretty much the same as the other one. So the coordinates, however, are going to be different from those of the reduced species. This is what I meant before. Okay, so so we have the tilde, we have this guy here. Now we could do the same thing that we did before to get the topology and coordinates. However, as I said before, and I'm saying it plenty of times, I want this to be really clear. We need different point charges for the solute, and we are gonna get them from a quantum mechanical calculation. Okay. Now, here is this guy here, the Redox.imp. This is this is, as a matter of fact, an input file for Orca. Now, there is a question in the YouTube channel which regards how many cores do I use per calculation. Now, in this case, the default is just one core, so we are not setting any cores here, so just a single core. The number of cores, of course, depends on the resources you have and depends on the size of your system and the computational cost. So it really depends a lot on what you have to do. But in general, for quantum mechanical calculations like Hartree-Fock, DFT, roughly speaking, these programs like Orca and other programs scale more or less linearly with the number of cores for up to 16 cores. Once you get to 16 cores, if you increase further the number of cores, the efficiency you're going to get is not as good. It's not linear. It's going to be less than linear. But yeah. Okay, so back to our system. So here we have the exact same geometry. So the x, y, z coordinates of the oxidized version of the ligand. This is the same thing that is in the PDB file. Okay, so here we have this guy here, then Hartree-Fock. So we're going to use the really well-known method Hartree-Fock, which is, well, of course, some of you might know that, yeah, this is not that good because it misses the correlation, the correlation part of the wave function. But we use Hartree-Fock basically because we want to be consistent with the rest of the force field that we're going to use. So remember that we have not only the solutes, but also the solvent, and our solvent are water molecules. Well, the force field that describes these water molecules has been obtained, well, the point charges with Hartree-Fock. Well, I mean, I'm actually not 100% certain whether that is the TIP3P or actually the gap, or both of them. But we use Hartree-Fock for the sake of consistency for some amber force fields that we tend to use for simulations with amber. This is the basis set. So this is the methodology. Hartree-Fock, then 631G. So this is the basis set of functions that we're going to use in each in the computation. So I want somebody to tell me what are these numbers here. So we have x, y, z, and then we have 1 and 2. What are these guys here? Could somebody tell me?
Charge and spin multiplicity.
Exactly. This is the charge, and this is the spin multiplicity, and they're going to be different from of course, from the reduced species. This is what's going to determine that we navigate, we explore, well, a different different potential energy surface. Do we have something else here? No. The input ends up with an asterisk, and that's it. So this is really, really simple. Okay, so what are we going to do? Well, we're going to perform the calculation. So we're going to call Orca. Okay, I'm going to submit the calculation. Please submit it, and then I will answer the questions. So we call Orca this way. Then we give it a name of the input, redox.inp, then this usual greater than the symbol. Redox, the name doesn't matter here. I like to call it the same way as the input, apart obviously from a different suffix, because otherwise it will overwrite your input, and well, yeah, it's not nice. Okay, so we'll do it this way. Computation should be running. It'll take like a minute or so. So you see there is calling Orca SCF. Let's see. Okay, yeah, so how many cores are used? I have already answered to that question. Okay. So yeah, of course, I mean, Orca is a really cool quantum chemical program because it gives you flexibility on the number of cores you want to use, the memory you want to use, and well, it allows us to perform quantum mechanical, molecular mechanical calculations. So we will see in a second how to, well, how to do so. A thing that I haven't said is that you probably will remember that there are several different QMMM paradigms. Well, in this case, what we are using is so-called electrostatic embedding. Okay, so we are polarizing the wave function of the quantum mechanical region with the point charges. So they enter the Hamiltonian as an extra Coulomb term. Okay, so in the meantime, we are going to need another thing. Let's take a look again at the files that we have here. Of course, since the calculation is being executed in the same folder, it's going to create a lot of junk. Well, let's take a look at how is the calculation with a tail command. So tail minus f, and it's going to give you, well, the tail of the file you're interested in. So okay, well, yeah, it finished. This is an SCF computation, which means that it is going to solve, I say Schrödinger equation. In practice, it's an approximation of the Schrödinger equations, which are called the Hartree-Fock equations, in an iterative manner. So in case you want to see how your computation is proceeding, I'm going to do this for completeness. So I'm sorry, I'm going to do it slower. So I have opened the output file, okay? There is going to be a section in the output file. So I'm going to go to the end because I don't remember what exactly the parser is. So I'll just look for this iteration section of the file. I'm just going to go upwards. You don't need to do this in also in your go further upwards. I think it should be SCF, total SCF time. Well, it doesn't matter. I'll just resubmit it again and then show it to you. In the meantime, we can do the other thing that we need to do. You don't have to resubmit it. This is just for my own sake. Let us, in the meantime, create a mol2 file like in the previous case. Now the mol2, remember, it contains contains the coordinates and the point charges. Now the difference here, of course, is going to be that we don't want the point charges because we're going to get the point charges from this file here. This we will do later on. So let's just do this tail stuff. Inp.out. Oh, okay. Never mind. Yeah, the tutorial is tricking me now. No, it took much less than before because Orca has this really nice thing that it reads the wave function that you have in your working directory, and it takes this as a guess for your new calculation. So that's the reason this time the computation took much less. Okay, never mind. Actually, if anyone in the chat knows what the parser is for looking at the SCF convergency, could write it on the chat to see how how could we do it. Yeah, so let us create in the meantime this mol2 file. So let's see what do we have in our directory. So we have this output, which is really important. We have the PDB, and so we already know how to create the mol2. We're going to use antechamber. So, perhaps you have already seen that well, I used to operate with Orca some years ago, but yeah, I haven't really taken it for a while. Okay, so the input is going to be the PDB that we have in the folder. So we are creating the mol2, okay? -o, then click.mol2. -fo mol2. I'm sorry, I didn't put the -fe before. The ordering doesn't matter, but for the sake of consistency, I'm just putting it this here. So this is the format. So PDB, the format of the input, PDB, PDB, OFO and atom type, which is GAF. I think it does it by default, but I still write it because I want to make sure that it does what I want it to do. Okay, as you can see, it took much less than the previous case. It doesn't have the SQM thing that appeared here. The reason is that we don't have point charges here. So again, it created all this junk. So antechamber, blah, blah, blah. I mean, it's not junk. It's important stuff, but not for us. So let's remove these guys here. Then ls minus LTR. These are the guys that we have in our folder. Okay, so here's the mol2. Coordinates. So we have the coordinates, atom types. We do not have the point charges. So what are we gonna do? I mean, we're doing things pretty manually here. Now I have put some steps to follow in the PDF, on which you can do this more or less manually with some kind of fancy commands with the VI editor. Now I have already put a mol2 file with the point charges. And what we're going to do is we're going to take the charges from the output file and we're going to put them instead of these guys here. Since I have a much smaller screen, I don't think if I show it to you, it's going to show too much because these things are going to collapse. And well, we could try it out, but the important thing is that we are interested in a mol2 file with the point charges now. As I said, I have already put a mol2 with the point charges we're interested in. They're going to be the same because the SCF is going to be the same. So it is here. It is called lig minus charge.mol2. If I did everything properly, then this should have your point charges. So this is the same file as before. As you can see, the coordinates, the x, y, z coordinates are the same. The only difference, of course, is that now we have the point charges. Now the question arises. I mean, well, nobody did the question. I'm doing it. But where did these guys come from? Well, they came from the hierarchy calculation that we did before. So let's open it up. It is this guy here, .imp.out. And okay, let's parse the string that we're interested in. So I think it is So with a slash, remember that when you go to slash, you get to this mode, the parsing mode. This is VI. This is the VI editor. If you have any other editor, of course, you're encouraged to use the thing you're most comfortable with. So we're gonna look for the Mulliken pop. Let's just look for Mulliken pop. I think it is this one, Mulliken population analysis. So it is gonna take us here. This, of course, is after the SCF was done. The SCF is the quantum mechanical calculation. You have the point charges down here. So we have Mulliken atomic charges and spin multiplicities. So as its name suggests, we're going to have each one of the atoms here, as usual. Then in the second column, we're going to have the point charges. Now, what I did was just manually copy this column here. I cannot highlight it so this way. So I'm gonna highlight it with the thing that is shown in the PDF. Do I have the PDF around here? Yeah, the PDF. Remember, the PDF is in this page. Yes, I just want to show you how you can do it manually. Of course, if you are more acquainted with making a program, script, or whatever, of course, you're encouraged to do so. But this is just for showing you where things come from. Okay, so this is the same thing. Here are the atomic charges. They're in this file. Okay, so of course, if you are a VI editor, so here are the steps. You can highlight and select columns from the VI by using this Control-V command in the other file. But yeah, this is what we did. So you have the lig minus charges.dat file there. Okay. So at this point, so this is the file we're going to use for TLIP. So since this is the input file for TLIP, TLIP.in, we're going to open it. It's going to be pretty much the same as before. Now, of course, well, we are importing the parameters we're using. I use the import word. I'm quite acquainted with Python, but yeah. No, I'm not acquainted. I just like Python, but I don't know. So, so here's the first important thing. So, of course, here we're loading this lig minus ox, but of course, remember that. I mean, if you didn't do that thing with the point charges, I mean, you didn't copy it, but instead just want to use the charge file. Well, change the name of this guy here. So instead of mul2, sorry, lig ox. No, yeah, it's called minus charges, right? So please either change the name as I did of the mul2 file, or rename the charge in your terminal. Either will just work. For us, it is important just to import these charges. So I want you to tell me. I think you're
Gustavo, I guess it's charge without S.
Ah, without. Okay, cool. Yeah, thank you. Thanks a lot. So it is charged without S. I did it and I already forgot it. Okay, so we're gonna bring them all too. We're gonna bring the lig minus ox dot frc mod. Then we have the solvation box. This is the same as before. Actually, the input is gonna be the same, the exact same input apart from the names, because they're gonna be called ox. And there is this guy here. Okay, let's see. There are two questions in the chat. Okay, from the channel. So why same? So why do all carbon atoms show different partial charges? All carbon atoms should have same partial charges, right? Yes and no, in a sense that yes, they should have the the same partial charges so long as their environment, basically their coordination, is the same. So, in other words, if the molecule has a high symmetry and the environment of each one of the carbon atoms is the same, then yes, they should be the same. One example is the ethane molecule, because you have CH3 minus CH3. So these two partial charges should be the same. In our case, I think each one of the carbon atoms has a different environment. So we can visualize it again, just to see why this is not the case. Okay, CD22. Sorry, I'm doing this quite fast. But, so I'm just opening. I'm going to open the PDB of the reduced species. So yeah. So for example, in this case, you could, in principle, think that, hey, why, for example, doesn't this atom? I'm gonna change the representation quickly. Okay, so here's our molecule. So why doesn't this atom here, carbon atom here, have the same charge as this carbon atom here? The reason is, yeah, this is a carbon atom, then you have double bond with another carbon atom. What happens here? Well, it happens that this carbon atom is bound to another carbon atom, which is, let's call it another sp2 atom, which is yet bound to another carbon atom. So this, we're intuitively, we can see it in terms of polarity. So let's just say that this guy here is not as polar, for example, as this guy here because of their environment. So in chemistry, we like to say there are different partial charges because the environment of this guy, so this guy is bound to an oxygen, and this oxygen attracts more electron density from this guy than the electron density that, for example, this other carbon atom attracts. So this is basically electrostatics. So you have different charges, partial charges, that attract a different amount of electron density. And as a reason, the environment of this guy here is different from the environment of this guy. Okay. If these were just an ethane molecule, of course, these two partial charges in principle should be the same. But this is not the case. Actually, we have no two equivalent carbon atoms here from an environment point of view. Okay, hope this answers the question. Okay, let's exit here. Let's go back to the input. Yeah, so this is basically the same thing apart from this add ions run. I'm gonna ask any one of you, why are we adding this guy here? What? So we're putting a chlorine minus atom. Why is that the case?
To neutralize, because we do not have a charge equals 0.
Perfect. That's the main reason. And actually, we're neutralizing the system. So actually, this is the syntax for neutralization in Amber. Now, this 0 here indicates precisely that. Now, if it just says neutralize the system regardless of the charge that it has. So if instead that we had a plus one charge here, we had a +2, we could write down the exact same thing at ions rand, mole, Cl minus 0, but instead of 0, this would be, oh, sorry, this 0 indicates please neutralize the system regardless of the charge of the molecule. So we are neutralizing. In this case, it's just going to put a single chlorine ion.
Gustavo, yep. I have a question.
Yeah.
So we are neutralizing because we have a box, right? Because if you are using like a spheric contour condition, then do you still need to neutralize this or no?
That is an excellent question. Actually, you need to neutralize the system regardless every time you have periodic boundary conditions. The reason I think stems from how you account for the electrostatic interactions, and especially when you use this Eval summation thing. But basically, like let's say kind of intuitively, of course you have a +1 box here, but then you have a +1 box here, and you're replicating this charge all over your periodicity of the system. And you would, in the end, have a kind of unrealistic description of the system, because of course, in solution, you don't have +1 solutions, you have a neutral solution. So this is the reason. So you would account for artificial interactions between this is the real reason. You would account for artificial interactions between the different boxes in your simulation. So this, of course, sorry.
Sorry. No, but this is because you are using periodic boundary conditions.
Yes.
If you are using just a sphere, like to solve the system, so
okay.
you still need this or no?
I mean, at that point, I mean, I would tell you, I wouldn't do that. But of course, I'm not telling you that one cannot do that. In the sense, it depends on the problem that you have at study and the methodologies you're using. So we do so because we have the periodic boundary conditions. That's the main reason.
Okay, thanks.
Thanks to you. Okay, next. Okay, so of course you will have realized that we do have this guy here, but we do not have this guy here. So we have to create it. This is easy peasy. Or easy peasy, I don't remember how you say that. We're going to use parm chk2 again. It's just a single command line. So parm chk2, so -I. Remember, we have this, where is it? So this lig minus charge.mol2 minus O. The output is going to be called like this one, lig minus ox.persimod, and the format, again, the format of the input file, which is mol2. Okay, so no errors, nothing, and let's see what we got. Lig minus ox.frcmod. You're going to notice that this guy is the exact same guy as before. The reason is because, well, yeah, it just looks for parameters that are already present in the Amber force field for different atoms. So it kind of says, okay, so we can more or less, when I say it, I mean like, yeah, the parm chk. So it looks for similar parameters in the Amber force field and says, okay, we can, in principle, accommodate this parameter. Like, I don't know, this could be, for example, an S. I don't know, I'm just guessing. And it accommodates it so that it reproduces the parameter that otherwise wouldn't be there in the Amber force field for our system. Yeah. Okay. At this point, we have all the ingredients again to generate the parameters, the topology file and the coordinate file. I'm sorry if this thing is a little bit repetitive. I tried to do one extra step here so that things were not exactly the same. Okay, so again, tlib minus f, syntax is the same as before. We already have the input here, which is tlib.in. And that's it, and hopefully it won't give any issues. Okay, so it didn't. Great. Let's see what we got here. So once again, it created the small minus ox dot the coordinates, the parameters, and the PDB to visualize the geometry. Yeah, there's not much to visualize here. If you want, you can, but it's going to be almost the same thing as in the previous case. The geometry is going to be slightly distorted, but yeah, it's not that fun. Okay, so let's copy the guys that we need. So mol minus ox dot, let's just copy everything at this point. Remember, with the star you can select everything. Let's do minus minus / We'll copy it in the run directory. And then we will go back there. And yeah, the drill is the same thing as before. So what do we have in the run directory? So we have the exact same amount of input files plus the run.sh plus the files that we have just copied there. So yeah, let's well, this we can visualize the run, but it's the same as before. So all the simulation commands put there sequentially. I'm sorry about this comment. Just ignore that. Remember, this is a comment, so this means that this line is going to be ignored. But as you can see, yeah, we again have a minimization, a heading, a classical MD, and then the QMMMD. So we're almost done for the first part. The second part is going to be briefer. So yes, well, in the meantime, well, let's run the simulation. So already know how to do that. Now have minus dot slash run ampersand. Okay. So we're there. Okay. Now, yes. Again, this guy is gonna take a little while to run. So in the meantime, do you have any further questions, comments on that? Otherwise, we can perhaps. I mean, if there are not questions, I'm gonna wait for 2 seconds. Otherwise, we can take a look at the input file, at the Orca input file generated by Amber. But yeah, let's wait. If there are questions. I'll drink some water. Okay. So we are the heating now. In this case, the heating is the part that is going to take the most in the simulation. Sorry about that. Because we're doing the most time steps here, because we want to attain for as much as possible the 303 Kelvin temperature for the production. So here it hasn't generated yet the Orca input. So let's just go quickly to the reduced folder where we have everything already. We have the inputs in particular. So remember that the QM input that it will have generated, of course, not here because it didn't work for me. Let's go to the other session. Sorry about this mix-up. So here it is. So this is the input. Remember, this is the QMMMD. And this is the input generated in this is the input for the last snapshot, okay? The Orca input. Okay, so it actually has some nice comments here. So most of these sections here are going to be introduced by this percentage symbol. So after the percentage, there's going to be a keyword, and within the keyword, there's going to be an option. Okay, so sometimes it has a beginning and an ending. For example, in the SCF case, so we choose the maximum number of iterations, which here is 100. Okay, there is a question in the chat. Can you please explain why you're repeating the simulation or what we want to find? Yeah, so we are Yes, as I said before, these steps are quite repetitive because, of course, here we're performing two simulations. Now, remember that our main goal is to compute redox potentials. So we have a reduced species and an oxidized species. So these are two quite different species, and as such, they have to be described in a different manner. Now, I guess I'm going to put the slides here, just this guy here. Let's skip the animations. Okay, so yeah, so we are performing one simulation, a molecular dynamic simulation for this guy here, which is the reduced species, and the other one for the oxidized species. So yeah, I'm sorry that this thing looked a little bit repetitive, but I think it is important to know what exactly you should do to compute this quantity here. And the reason is because the Gibbs free energy is going to be a difference between the averages of the energies of the two simulations. Now we're skipping this guy here. It's just a constant. It's not gonna do anything for us today, but of course you should consider it when publishing. Okay. So yeah, that's the reason why we do a simulation twice, because it's not that we do it twice, it's that we are actually doing two different simulations. So the force field here in principle is different from the force field there. Okay, thanks for your question. What else? Let's see. It's sorry, of course, I'm in a different place now. So let's see how we are doing here. Okay, so this is the reduced. So I'm going to go back to the oxidized folder just to see how the simulation is doing. So it was oxidized, of course. Okay, great. It's still doing the heating. Let's see at what time step is. So let's do this magic. So tail minus F, heat that out. I think it is 3,000 time steps. It's still going to be a couple of minutes more. The good thing, you can see that it is getting to, hopefully, it is getting to the temperature we're interested in. Okay. So at this point, yeah, I'm gonna skim through this section because here the steps are the exact same as before. So I'm not gonna analyze again the output. Remember that it will generate this. Well, this. I'm gonna come here again. It will generate a QMMM.out, which is the file of interest. So please, once your simulation is done, it's just a single step. Do the grep of the externe SCF stuff as we did before, and generate the energies.dat file. This time for the oxidized species, you will see that the energies are going to be different here, slightly different. Okay. Okay. The last step is going to be the easiest one, because it's just going to be to execute a script. But of course, I would like you to see what the script is doing. What are we actually doing? So I guess I'm going to take this opportunity to show you how are we actually going to compute them, to compute this Gibbs free energy of oxidation. Unless it has already finished, which it hasn't. So remember, we are here. Okay, so of course, remember that you have to do this once the simulation is done and once you have ensured that you have this QMMM.out, which we haven't. Do the grep, then externe SCF. It doesn't make sense that I already down here. It's written in in the instructions. So let's take a look instead at the script that we're going to use to compute the Gibbs free energy. So let's go 2 steps backwards. Okay, remember we are here, 1 QMMM, oxidized, 1. So we are at this point. So the 1 QMMM and D, and we have the Gibbs.py guide here. An important thing, I will show it also because we will also use it for the second part, because in the second part we will compute the Gibbs free energy in pretty much the same fashion as we're doing here. Now the difference is the way we're attaining, we're fetching the energies. Okay, this is a Python script. Yeah, the only thing that it will require is NumPy. So NumPy basically works with, for those who are not acquainted, it works with vectors. Oh, it's called arrays, but in our case, we're just going to be interested in 1D arrays, which are basically vectors, so lists, you can call them that way. Okay, so the first thing is, it is, well, here we define 2 variables. Which are giving me the path of the files containing the energies. So we're calling ox, the file energies.dat that contains the energies in a column, the oxidized energies. This is what we will obtain in just a second. And the same thing for the reduced. So these are just two files. Then we're gonna use this NumPy stuff. So what we are doing is we are creating 1 array, so or 1 list for the energies of the oxidized state. So suppose that they're gonna be written like something like that. So for example, the first energy is minus 23,456, then the second is minus 3,567, and so on and so forth. So this guy here, this EOX, is going to be a list containing these values. Let's cancel all this thing. So we have 1 for the oxidized, 1 for the reduced. So what we have in this variable is basically, let's go back to the presentation. So we have this thing here. So the first, I'm sorry if I'm being slow here. Of course, in the premise, it's not, the people need not know how to program, which is perfectly fine. So just to actually see what's going on. So we're going to construct like a list, like this one here, with each one of the energies. So 1 for the oxidized species, so for the QMMMD for the oxidized guy, and the other one for the reduced species. So these are these 2 commands here. Yeah, I wanted to print out the arrays here. I didn't, but of course we could like print it here. Now this is a script, so this is actually not executing. When it finishes, we will execute it. We will get a value, and yeah, eventually we can also do that interactively. So it's easier to follow. Okay, so yeah, we have these 2 lists, 1 for the oxidized, 1 for the reduced. Then Python is really nice because it has things pre-implemented, like average. So if you do this numpy.average in the oxidized species, it gives you back the average value of the oxidized species, which is precisely precisely this guy here. Well, this guy here. It also gives you this guy here for the reduced species. And once you have the 2 averages, once you have 2 averages, which are these 2 guys here at ox and break, we compute the Gibbs free energy as follows. It's just the difference, right? Now the thing is, I'm multiplying this difference by this conv, which is a conversion factor, because this is something I didn't tell you before, but Amber gives you as output the energies in terms of kilocalories per mole. So we just transform these from kilocalories per mole to electron volts. Why do we want electron volts in the case of redox potentials? Well, one volt. What is 1 volt? 1 volt is basically the electrostatic potential generated by a single electron. And I mean, everybody knows what. Well, I hope most of you know what the voltage is. So it's the voltage of a unit charge. In this case, we are stripping a charge from our molecule, and therefore, this is basically the energy of stripping one charge. We are using this as the unit of measure. So this is actually an energy, let's say, per unit charge. So now our process involves a single electron, and therefore the energy in electron volts is going to be the same as the voltage, or it's going to be the same as the potential difference, the delta E that we saw. Okay, I think the simulation should have finished. Of course, it is going to print the Gibbs free energy. Yeah, and I think it finished properly, which is fortunate. Did it also finish for all of you? Let's make a fast stop. Okay, so yeah, you have the output. So please do the graph that we discussed before. Where are we? So we are we are here now. So we are in the 1QMMMD. Of course, this should be your username. Sorry, not the username, but your name, your actual name in your cases. So let's go back to the reduced run. And you have the QMMM.out. I already have the energies.dat here because, well, but yeah, it's just that web command. Externe SCF, QMMM.out, then energies.dat. Sorry, don't execute this yet. This energies.dat. Once again, please remove the last 2 lines of this file for the same reason that I explained before. Because we have to remove the RMSD and also the average. And the average, we're going to compute it again for our own purposes with the script we have just analyzed. Okay, once you have this thing here, the energies.dat, we will go back to steps. And what we're going to do is the following thing. So yeah, just execute Python. If you have Python 3, well, Python 3, or depending on how you've called it in your installation. Then gibbs.py. And hopefully, if I didn't mess up anything, it will work. Let's see what it gives us. Okay, so let's just take 1 second to look at this number. Now this is 10 electron volts. This is a lot. This is way too much for a half reaction. Now in practice, when you have a redox reaction, you have one of the half reactions, which is the one that I showed you at the beginning, but afterwards you have, let's say, a complementary reaction. So if you have an oxidation of one species, you will have the reduction of the other species. Then when you add up those 2 things, you have the overall reaction. So usually when you compute half reactions, that is simply the oxidation process here, and that's it, you get a potential, which is the potential of half. It's called half cell. Now this is already way too large. because when you obtain whenever you want to compare oxidation potentials, let's call them redox potentials, with experimental data, that half a reaction is combined with a reference electrode, which has an absolute potential, let's say. So, for example, the electrode of, I think the standard hydrogen electrode, I think it's minus 4.44 electron volts or something like that. So if you want the comparison with the experimental value of this half reaction, you have to subtract this thing to this thing here. So this is going to be minus 6. Now, this is a lot. But please bear in mind that we are doing several approximations here. First one, we are running for a very, very short time, simulation time. It's overall like 1 picosecond. Sorry, no. Well, what am I saying? For the QMMMD, we have run for just 200 femtoseconds. And remember that this is usually the tail that we discard when we get actual production data. The simulation must be way longer, like at least 5 picoseconds, because you have to discard the data that needs to work considering. The second thing is to see whether you're actually running at the right temperature and whether you have actually equilibrated your system properly. So let us just take a look a little bit at, for example, the reduction, the reduced run simulation. So we go there, we open up let's open up just the heating, heat.out. Let's go all the way down. Let's look for, so up, look for the final temperature. Okay, so this is okay. Well, kind of. I mean, it seems that we got up to 294 Kelvin. The reason is, well, we didn't provide too many time steps to the heating. So this is just to point out that simulations, even the classical MD simulations, need to run for longer time, for longer simulation times. This is really important. Perhaps this is the most important factor in this case. We are not actually running at 303 Kelvin. So yeah, this is bad. Okay. I think this wraps up the first part of the tutorial. The second part is going to be shorter, I promise. But yeah, we have 2 simulations, one in the oxidized and one in the reduced species. Okay, so at this point, we can now go to the part 2 folder. Okay, of course, before we go ahead, are there any questions, comments, perplexities? I don't know. Let me know. Okay, so let us make a PWD again. We're in this part here, tutorial 2 QMMM. What's going to be the difference between this case and the first case? Could somebody tell me what will be the difference? It's either we're using a different force field, or you can also type down in the chat. It's however you prefer. Just to see what do you think. So what's going to be different here? So with respect to part 1, I'm gonna put this slide here again, because this is what actually says it's going to change. So we were here. So we perform, okay, of course we perform classical MD, but then we perform a QMMMD, and this were the data we were interested in. Now, in this case here, don't worry, we're not going to prepare again the system. I have already provided you with some trajectories, which have been run for 10 nanoseconds. So how could we attain 10 nanoseconds? Could we do that with QMMMD? One could, if one had very, very powerful computers and a lot of computational time to spend. So in the second part, where am I? Here. So in the second part, we're going to use some previously generated classical molecular dynamics trajectories. Okay, so there, the actual geometries that we considered were obtained with a classical force field. Of course, the computations were cheaper. I ran them for 10 nanoseconds, but we still want to do QMMMD. So sorry, we still want to get QMMM data, but this time we're going to perform single point calculations. Okay. So we are now here in this QMMM single point folder. Here we're going to use this the mobile tools thing. So what we're going to do is we're going to take the trajectory. We'll go back to the slides because they show things that we're doing. So we take the trajectory, we get some snapshots, that is some geometries out of the trajectory, and then we do an energy calculation on top of each one of these guys. So the very first difference here with respect to the previous method is that we are so we are in a longer time scale. We're in the time scale of nanoseconds, and yes, if you wanted longer simulations for the QMMMD, you would need many more computations for each one of the time steps. Okay, so let's. It really isn't going to change anything if we do either of them. So for the sake of simplicity, let's say let's do the reducing. In the end, our goal is to generate another energies.dat file. So let's go to the reduced part. What do we have here? Okay, yeah, sorry, this is not the right folder. These are spoilers. We are gonna generate all these folders, but for the time being, let's assume we do not have them. Okay, so here are the 4 files that we're gonna require. Okay, here we will use mobile tools. So if you have installed them correctly, the best thing to know whether you have them or not is to execute the main script, which is called main, our original, qm inputs.py. You should have the auto completion here. So main.qm inputs.py, then let's .py, then use the -h option. Okay, so the program is going to take 2 inputs, a main input file, which is called main here, and a template. Okay. Let us take a look at each one of those. So the main input file is introduced with this ampersand main, then end. So here you have these different options here. Okay, so you will have to tell it what software are you going to use for the quantum mechanical calculations. Now, an important thing is that you actually don't need to have installed the software here. You can generate the inputs in your PC and then copy them somewhere else and then perform the actual calculations there. So you could even generate the geometries in your personal PC, like I'm doing right now. I'm not, but I could. So here we're going to use Orca. I mean, we're going to generate Orca input files. Then we tell it what is the topology we're going to use. So you have a topology because you need a trajectory, but you also need the parameters. Then you're going to give it a trajectory because we're going to fetch, in our case, 100 geometries out of this trajectory. Now, here's an interesting thing. So here you have a QM mask. Okay, so once again, we have to define which atoms of the system are going to belong to the QM region. This is 2.1, but in this case, yeah, you can do the same thing as in Amber. And then the number of geometries. So these are actually the indices of the geometries. So here we have 100 geometries. And in this option, we can tell it to start from a certain index. So 0 is going to be the first one. And the last one is going to be 99. So this is a range. This means go from 0 to 99. But if you wanted to generate just a single geometry, you could just remove this thing here. And you can choose whatever geometry you want, like 54, for example. And this will generate a single input file. Okay. This is the main input. So these things are general. So you can use this input for whatever software you wanna use afterwards. The only thing you have to change is this thing here. The second one is this tpl.imp, which is kind of a template file for the QMMM, which kind of has the same syntax as what you would actually do for a specific input file. Of course, the advantage of this method is that it is going to generate 100 input files, but it is going to change the geometries and the point charges, and most of the other settings are going to be kept. So in this TPL, you have the header. This header is going to contain what usually people like put it at the top of an input file. So in our case is this exclamation point, then XTB. So basically we will want to perform an XTB computation. This extern CHG indicates that we want to consider point charges of the system. So not only the QM region, but also the point charges. So you might consider why. I mean, why shouldn't I consider the point charges? Well, there might be some situations in which you are actually only interested, for example, in a specific portion of the system. So you want to perform QM, like you want to get 100 inputs, but prescinding from the point charges for whatever reason. For example, instead of the point charges, you would like to use implicit solvent. So of course, if you want, for example, implicit solvation, you put it somewhere else here. For the time being, yeah, let's not do that. But there is the possibility. And finally, this CHG spin indicates the charge and the spin multiplicity of the QM region, just exactly as the case of Amber. Okay. Now, these mobile tools stuff can do some other things, but yeah, I'm not going to cover them today because, yeah, because I don't think we have too much time for that. But of course, if you're interested, you can write us, or you can also ask in the chat if you want. So what do we do at this point? So we have seen the main input, the template. Let us now generate the inputs. So how do we call the program? So as before, main QM inputs.py minus I. So the input is going to be called main. Yeah, sorry, just one thing. In the PDF, I think the main.imp, this guy is called MD instead of mol. I corrected it on the input files that I have provided you, but nonetheless, please bear in mind this thing. Sorry, I'm actually missing one thing. And this is actually really important thing. It's also written in the tutorial. So we have an MD trajectory here. The problem is, of course, the way this trajectory is shown depends on how Amber has printed the output. So sometimes, I mean, you can tell it in the input whether you want all the molecules printed on the primitive cell, so on the first cell in your periodic boundary condition box, or not. Of course, the simulation runs considering these periodic boundary conditions, but whatever it prints you as output, like whatever you see, this need not be the case. I think Vito talked about that in the very first session. And for this reason, when you perform these single point QMMMs, it is very important that you image your trajectory to the first solvation, to the primitive cell, you know, because here you're not gonna have periodic boundary conditions. You will perform a single point and you will consider all the entire system in your computation. You will not have the periodicity that you had before. So we're going to use CPP trash because this is the easiest way for doing so. So let's do it. So CPP trash, and let's load the parameters. Actually, you can actually already start CPP trash by having loaded the parameters, but I always forget how to do that. So I just load them in command line like this. So molred dot prm top, then trash in this guy here, then auto image 0.1. So we're anchoring the first residue, so we're putting it at the center of the box. Sorry, I think it is yeah, 2.1. Then trash out. We are gonna call it red minus im.mdcrd, simply because this is the way I called it in the main.input, but you can call it whatever you want. Okay. Then go. Then exit or quit. So we have it here. It has the same size as before because yeah, we have the same amount of atoms as before. We have just moved everything to the box, to the primitive cell, and now we can execute the mobile tools. Main minus qm inputs, so minus I main input minus p the tpl dot, sorry, minus t. If you want, you can create an output file because it's gonna print a lot of junk here, but otherwise yeah, this need not be the case. So it's gonna take a little bit. So yeah, it will generate overall 100 inputs. The indexing starts from 0, but from 0 to 99, still 100. Okay. Yeah, let's see how long is it taking. So well, there are still some processes running. Yeah, after that, yeah, we will just see one of the inputs, and yeah, we can submit the calculations with a single script. in sequence. The good thing is that with XTB, with the Orca interface with XTB, these computations are really, really fast. So we will have all 100. Okay, let's see. Well, I think it has done something. Okay, it has done its job. Good. Yeah, so as you can see, we have 100 different folders. Each one of these folders is going to contain each one of the input files. They're going to be quite simple. So let's go, why not? For example, 319, geometry 19, because why not? So what do we have here? So we have the actual input file, which is geom19.in, which is extremely simple. So again, there's nothing different from. Of course, there are far less options that with the Amber input, because I'm just using the defaults here. You can, of course, set them in the template file. If we go to the end, as you can see, there's also the option of point charges, and it will create a file called charges geom19.xyz. So whatever appears here is the QM region that you chose. So this is the 2 points, the column 1. These point charges is the rest of the water molecules. Now, if you chose 1, 2, then you would also have, for example, 1 water molecule here, and it wouldn't be present, of course, in the point charges file. So this is the other file that is generated, right? Which is here. So yeah, to complete this, we can take a look at it. So the first column should be the point charges. So this is point charge number 1, and then the XYZ coordinates of that atom. Remember that each point charge here represents a specific atom in the MM region. So, well, the way of executing, of submitting each one of these calculations is Orca, because you always call Orca, then geom19.imp minus geom19.imp.out, the ampersand, but I think it's not gonna take too much. And yeah, it performs the calculation. Of course, you're not gonna do this thing 100 times. I have put a script on the tutorial. It's actually open there. So this is a bash script which is called submit.sh. I'm sorry I didn't put it in the GitHub. I think neither there. So I think we can just copy and paste it, hopefully. Otherwise, well, I've read it from scratch. It's not a problem. So we can submit in as a sequence all the calculations from the reduced folder. Let us generate the submit.sh file. So I for insert, and then we paste things here. Yeah, it did some weird stuff. So for so here we're doing a for loop. So basically, we're going to iterate through this range from 0 to 99. I just like to indent things because to see them more nicely. But for this scripting or programming language, this is not necessary. It's bash. Okay. So we are going to enter each one of the geometries. Then we are going to perform the computation that we have just done. The format this thing properly. And yeah, and so it will perform these computations sequentially. Now it is going to be quite fast. It will just take 200 milliseconds per computation. So let's do it. I'm gonna do it using no hub because why not? No hub. Submit sh. Let's hope this doesn't give issues. Okay, yeah, of course, because it doesn't have execution permissions. Great. So please execute this command in command line. So the file is yours after all, but chmod a pu rwx. This is the way of changing permissions for everybody of a specific file. A stands for all, plus stands for enable, read, write, execute. So just the X is sufficient, but yeah, let's do it that way. So this is the command in case you copy pasted it. Where are you? You cannot find. Okay. The chat. So I'm gonna put it here, and then I'm gonna put it in YouTube, and afterwards, so you can execute the script, and it is gonna execute. Okay. So yeah, as you can see, it is really fast. So as I told you before, what's the difference between doing this and doing QMMD? From a computational time point of view, to arrive to even 1 nanosecond of simulation, if your time step is 2 femtoseconds, you can do the math. How many single points did you have to do there? Like 500 at least. No, 500 times 1,000. A lot, too many. And each one of these computations is still more expensive than an energy calculation with a classical force field. So in this way, you already have the geometry. So all you have to do is perform 100 single points with QMMMD. Sorry, with QMMM. Sorry, I'm creating a lot of confusion here. Okay, so as you can see, it has already been done because it's just 100 QMMM single point computations. And yeah, the last thing here is to generate the energies.dat file. So we're going to do this for the reduced species. So let us see what do we have to look for in this case. Actually, I think it is written in the tutorial. I don't remember. Okay, so here it is. So we're going to look for this string in the output file because this is a string that will contain the SCF energy. Okay, final single point energy. In.out, if it did it properly. Okay, it did it with a space. That's not good. Yeah. Okay, let's put it on a string. We'll open it. Okay, so here it is. And this was because of the way I wrote it on the output. But yeah, so we're going to look for this final single point energy. And we're going to grab these things from the output files. Okay, so you can do it automatically for all of them. So grep geom star, which indicates please look for it in all geometries. Then geom star.out. The output is going to be energies.dat. See if it actually did it. Okay, it didn't do it. Ah, of course it didn't do it because of the name of the output. So it should have done it. Let's yeah.
Yes, there is an extra blank space. Yes, yes.
Yeah, that was a problem before. So let's just run this again.
You forgot the name of the input file after grep.
Oh yeah. Actually, on the contrary, I forgot the name of the string. Of course.
Yes.
Sorry about that. So final single p. I think that this will be enough. Just one star. Okay, here it is. So yeah, this space, this is not good practice. Sorry about that. Okay, so here are the energies. The energies.dat file is going to be slightly different from that of the QMMMD, but you have the exact same information. Now, at this point, I tell you that you should do this thing again, but for the oxidized state. It's literally the exact same thing. Now, the only things that are going to change, of course, are the charge and the spin multiplicity and the template file. So since this is already quite repetitive, I think we can wrap up here. And yeah, I think the computation at that point is going to be the same. So you will also have to use the gips.py script. But remember to do this thing for the oxidized species. Okay. So yeah, I think we did it for the reduced, remember? Still have to do it for the oxidized, but I think we can wrap up here because I think everybody will be perhaps tired. It's been a lot. Of course, if you have any questions again, you can ask. Yeah. Otherwise, we can finish the lesson for today. Let's see. Okay, the YouTube channel, there are no questions. In the chat, no. Okay, I think then we can wrap up for today. And remember that next time. Oops, sorry. Yep, here I am. So next time, what we're gonna do is we're gonna compute absorption spectra. So the good thing there is that we are not gonna have this to perform this thing twice. So it's not gonna be as repetitive. So yes, hopefully it will be briefer again than today's lesson. Okay.
Okay, so I'm going to stop the broadcast in YouTube. 1 second. So you finished, right, Gustavo?
Yeah. So
for today at least. Okay.
Bye the YouTube people.
Yeah, bye.